Good evening. We are in the ninth week of our problem solving session, and today we are going to discuss about this Fermi-Dirac statistical and Bose-Einstein statistical, and we will solve some questions. I wait for a few minutes and then I will start. So today we are going to solve some questions that were the concept was taught in the class week 9 in the week 9 by Professor Sandeep Paul and myself Subham. I'm TA for this course, thermodynamic classical to statistical. So we will start with this Fermi-Dirac statistics and Bose-Einstein statistics. After that we will solve some questions. So am I audible? So let's just start our session. So let's start with Fermi-Dirac and Bose-Einstein. We are studying this for identical and indistinguishable particles. So we know that this. Let's start with this wave function psi. Psi is a wave function for, let's say, n number of particles, 1, 2, 3, 4, and so on, up to, let's say, n. Okay. And if we operate on operator, let's say p is an operator, p 1, 2, this operator, while this operate on this psi, this will this will change the spin of these particles. Let's say this is the operator. So position of the particle, this will change the position of particle. Let's say p, we have applied it on psi, so it will either give us minus of psi or plus of psi. Here 2, 1 particle have changed their position, first and second particles have changed their position, 3, 4, and so on. Similarly 2, 1, 3, 4, and so on. So such particles are known as, these are where we get the minus sign in front of psi. These particles are known as antisymmetric. And this wave function, this is symmetric wave function. So there are two type of quantum particles. One is boson and other is fermion. So boson have this symmetry property. Psi for boson is symmetric, and for fermion psi is antisymmetric. Okay. Now we know that there is these are the quantum, these distributions are the at the quantum level. While we talk about classical, there is another type of distribution. This is Boltzmann. So this Boltzmann distribution is classical distribution. So when this temperature is very high, or the system is very less dense, then it will follow classical Boltzmann distribution. So we know that fermions are nothing but these are the half integral spin particles, like 1/2, 3/2, or 5/2, and so on. These are the spin for these fermions, and we know the most famous example is electron, having spin plus half and minus half. And there is another very interesting property of fermions. They follow the Pauli exclusion principle. According to Pauli exclusion principle, no two particles can be in same quantum state. So this is the Pauli exclusion principle. On the other hand, boson, they do not have any restriction. They do not have any restriction on how they are arranged. Like they can have any number of occupation number in one state. They can occupy as many particles can occupy single state as they can. So this is the boson, and they have integral spin. Okay. So now we will calculate this average particle number of average particles and this partition function, average partition function. So average partition function is equals to, at Fermi-Dirac and Bose-Einstein, is equals to multiplicative over k 1 plus minus lambda e to the power minus beta ek to the power plus minus 1. So this plus sign is for Fermi-Dirac and this minus sign is for Bose-Einstein. Similarly, for average number of particles, denoted by n is equals to, for Fermi-Dirac and Bose-Einstein again, this is equals to summation over k lambda e to the power minus beta ek divided by 1 plus minus lambda e to the power minus beta ek. So these are already taught in the class, solved in the class. So I'll just quickly write this formula and then we will move to the question part. Now the ideal Fermi gas. So for ideal Fermi gas, one very important formula is function, Fermi function for E at E is equals to 1 over e to the power beta E minus mu plus 1. This is for ideal Fermi gas. So this mu is nothing but this is the mu when this is equals to Fermi energy when temperature tends to 0. So we can write it as limit T tends to 0 mu at temperature T is equals to EF. So at when temperature tends to absolute 0, this mu T is the Fermi energy. Okay. So this mu T will become Fermi energy. So this Fermi energy wait a minute. So we will discuss this function Fe at absolute temperature T is equals to 0. Give me a minute. not working. Give me a minute. Okay, now it is working. So we were discussing about this Fe. There's some problem. So this Fe, this is nothing but this 1 over e to the power beta E minus mu. Mu is Fermi energy at absolute temperature. So at absolute temperature, at T is equal to absolute zero temperature T is equal to 0 Kelvin, this beta will become, beta is 1 over kT. So this beta is becoming infinity. Okay, so at temperature T is equal to 0 or beta is equal to infinity, there can exist only two value of Fe. One is 1 and other is 0. So its occupation can have only 1 or 0 at absolute temperature. We know that not more than one particle can occupy this state. So this occupation is either 1 or 0 at energy E. So the function will look like this. Okay, so 1 or 0. This point is E is equal to EF Fermi energy. So when the energy E is less than EF, this region, so it will have occupation number 1, and when E greater than EF, then it will have occupation 0. Okay, it will either have occupation 1 or 0. When energy E less than EF, then it is 1, and when energy E greater than EF, then it is 0 at absolute 0 temperature, 0 Kelvin. Okay, what make it different from the ideal gas? Like this is the Fermi gas. What make it different from the ideal gas is that at absolute 0 Kelvin, ideal gas will have no energy, zero energy. But this Fermi gas had some energy. That energy may arise from this repulsion. Like we know that only one particle, one fermion can have one quantum state. Like all the quantum states for two fermions cannot be same. All the quantum numbers, all the 4 quantum numbers for a fermion for two fermion cannot be same. So in one state there can only be one fermion. Otherwise there will be an energy repel that they will repel each other. So there is some energy even at 0 Kelvin. They cannot lie at same quantum numbers. So there is some energy that is repelling them. So there is energy in this Fermi gas, whereas ideal gas do not have such energy at 0 Kelvin. So there is an effective repulsion between fermions. Now energy what energy is there at temperature T is equal to 0? This is equals to 3/5 n EF, and EF is the Fermi energy, which is equals to h cut square by 2m 6 pi square by 2s plus 1 as is spin n by v number density whole to the power 2/3. So this is the Fermi energy, and this Fermi energy is inversely proportional to the mass. So as the mass of the fermion increase, the Fermi energy also decrease. So this is the inverse relation. And if T is low, if temperature is low but not equal to 0, it is near 0 but not 0, then f of Fermi energy, f is equals to, at let's say case, we consider one case, if E is equals to mu, then this will be equals to half for all temperatures. Just this temperature is low but not 0. Okay. So now we can summarize this about this Bose-Einstein and Fermi-Dirac distribution, and this boson and fermions we can summarize in one page. So comparison between distributions. So comparison, there are mainly three type of distribution. One is Boltzmann, one is Bose-Einstein, and one is Fermi-Dirac. So this is classical. Okay, so we know that the number average of particle is 1 over exponential of E minus mu by kBT. This is for Boltzmann distribution. For Bose-Einstein, this is equal to 1 over exponential of E minus mu by kBT minus 1 for Bose-Einstein, and exponential of E minus mu by kBT plus 1 for Fermi-Dirac. For these are all for indistinguishable. And for Boltzmann, spin does not matter. For Bose-Einstein, spin is integral. And for Fermi-Dirac, spin is half integral. Half integral spin. Now about psi. Psi does not classical psi does not overlap. Does not overlap. Because particles are localized. In Bose-Einstein, psi overlap, and in Fermi-Dirac, psi overlap. Here psi is symmetric, and for Fermi-Dirac, psi is antisymmetric. So these are the occupation can be does not have any restriction. So there is no restriction of how many particles are going to be in one state. So for Boltzmann there is no restriction of particles in one state. Similarly for this Bose-Einstein also there can be unlimited particle in one state. And for Fermi-Dirac there can only be one particle in one state. So Fermi-Dirac has one particle in one state, so they are restricted to this property. Okay. So the example for this Boltzmann classical distribution is gas molecules at low density. Gas molecules at low density, and these are example for this is photons. Photons are boson particle. These are boson, obviously these are boson, and these are fermion. Fermions follow Fermi-Dirac statistic, and boson follow Bose-Einstein statistic, and rest all follow classical statistic, that is Boltzmann statistic. And these Bose-Einstein and Fermi-Dirac also convert to Boltzmann at low density and high temperature. Example for Bose-Einstein distribution are bosons like photon, like helium atom or helium nucleus also. How we know this, like helium is a boson? We need to just look into the particles, and if there are there are even number of fermions in it, then they are boson. Like this is boson, but it has 2 electrons and 2 neutron and 2 proton. So there are 6 fermions into it, so they are bosons, even number of fermion. So even number of fermions are also bosons, and fermions are electron, proton, neutron, these are all fermions only. Okay. So now we can solve this assignment number 9 easily by using the concept that we have just studied. I don't have much questions for this week because there are not many available in the books, and this is an easy concept, so question in the assignments are also easy, so we will quickly solve it and then we will revise the thermodynamic formula later. So classical thermodynamics formula later, and because the statistical we are discussing from last 2-3 weeks, so we will discuss thermodynamics, classical thermodynamics formulas only after that. So we have 6 questions, so we will finish these questions and then we will move to the next one. So consider a very simple gas made up of 2 identical particles. Wait a minute. So consider a very simple gas made up of 2 identical particles. Suppose that each particle can be in one of 3 possible quantum states. In case of Fermi-Dirac statistics, what will be the probability of having both particles in same state? So we have just discussed that fermions have this one restriction, they can only have one particle in one state. So they can only have one particle in one state. This Fermi-Dirac statistic, fermion follow Fermi-Dirac statistics, and they have this property, one particle in one state. So the probability of having 2 particles in same state is 0. Probability of having two particles in same state for a fermion is 0. So it was very easy question. So this is the answer. Now we'll move to the next question. So the Fermi function Fe is given 1 over e to the power e minus ef by kBt plus 1, and they're saying that this is giving the probability of occupation of electron per energy state. Okay, so occupation, it will give occupation of per state, then the probability of number of electrons at absolute temperature T is equal to 0 when E is equal to EF is. At E is equal to EF, so I think there should be a correction in this question, like they should give this question as then the probability of number of electron at near zero, not absolute 0. So near 0 we can understand this, but absolute 0 I think I will consult with sir, and if you have any problem you can ask me in the next question, next session, but I think there should be near 0. So at near zero temperature, near 0 Kelvin temperature, 0 Kelvin near 0 Kelvin temperature, when E is equal to EF, then this F of E is equals to 1 over e to the power E minus EF upon kBt. So at any temperature T, but it should not be very higher temperature, because at very high temperature it will follow this Boltzmann statistic, and gas will follow Boltzmann statistic. But at any value of temperature T that is close to 0, not very high, this Fe will be this E minus EF is equals to 0 because they are equal. So it will become e to the power 0 plus 1. So this is nothing but 1 over 1 plus 1. So this is 1 over 2. So that we have discussed also, that at E is equal to EF and near 0 temperature, this Fe is equals to half. And also in the class, sir showed that graph also. I'll show it in the last slide. This is at temperature T is equal to 0 Kelvin, and other are like this sorry. So this is for rest. This is the type of curve. So actually I'm not making it correct, but let me make it again. So this is 0 and this is 1 occupation number, and this is the half, this value half, and here this is the E is equals to EF, energy E. So this point, this is for temperature T is equal to 0 Kelvin, this one, and this is for all other temperatures, temperature T which is not equal to 0. So at E is equal to EF, its value is half, occupation number is half. So this is the correct option, but this should be for near 0 Kelvin. So now they are saying that using the Fermi function of the above question, okay, Fe, evaluate the temperature at which there is 1% probability that a state with an energy 0.5 electron volt above the Fermi energy will be occupied by an electron. Okay, they are saying that this state is 0.5 electron volt above the Fermi energy. So we can say that E minus EF is equals to 0.5. And what else? The formula for F of E is given, that is equals to 1 over e to the power E minus EF by kBT, 1 over exponential of E minus EF by kBT plus 1, and by substituting the value we can get this temperature which is needed to be calculated, evaluate the temperature, and probability is given. Probability is 1%. So 1% is 0.01. Okay, 1 over 100. So this is 0.01. Let's calculate it quickly. So we just need to put these values in the formula and get the answer. So now we have E minus EF is equal to 0.5, and we have F of E is equals to 0.01. So and the formula is F of E is equals to 1 over exponential of E minus EF by KBT plus 1. By putting the values here, we can quickly calculate the answer. So f of e is 0.01, that is equals to 1 over exponential 0.5 divided by kb is, this is in electron volt and this conversion is given here. So by multiplying it with 1.6 into 10 to the power minus 19, this will become joule, and we know that k is 1.38 into 10 to the power minus 23 joule per Kelvin, and temperature we need to calculate plus 1. So we can take it to the other side and this will become 0.01 of exponential of 0.5 into 1.6 into 10 to the power minus 19 divided by 1.38 into 10 to the power minus 23 into temperature T plus 1, that is equals to 1. So we can solve this middle part. Zero 0.5 into 1.6 divided by 1.38 and multiply by 10 to the power 4. So this is 0.01 into exponential of 579.71 divided by T plus 0.01 is equals to 1. So this quantity will go that side. So it will be exponential of 579.71 divided by T, that is equals to 1 minus 0.01 divided by 0.01. So this is let's take ln both sides. This is 99, and by taking ln both sides, this will be 579.71 by T is equals to ln 99. So T is temperature is 579.71 divided by ln 99. I think I made some mistake here. Okay. I will solve it again. 10 to the power 4, 0.01 into exponential. This will go that side. And the formula is plus. Okay, I'll calculate it again probably. So this is kBT and this is 0.5 into 1.6. okay, this is the energy. So up to here it is all correct. Let's quickly calculate it again. This is 0.579 into 10 to the power 4. Okay, so this was 597 0.1. Sorry, I made a mistake here. So this was 97.1. 97.1. This is 5797.1 divided by ln 99. So ln 99 is 4.59. So 5797.1 divided by 4.59. This is 1262.98 approximately 1262.98 Kelvin. Though the option 1 is correct here, it's, as we are taking too much approximation, so option 1 is correct. It is very near to the answer. Question number 4. In which option all are boson? So we have discussed that boson, this photon or even number of fermion. These are the bosons. So first option, electron is not a boson. Photon is a boson. Nucleus of 2H it should be a boson, because the nucleus we are only talking about nucleus. So nucleus of hydrogen has only one proton, 4H2, one proton and one neutron. So two fermions is a system, all the system is boson. So 2H is boson. Similarly, nucleus of Na, these are 22 particles, so again it is a even number, so it is also a boson. Nucleus of O2, oxygen, again it is 18, so again it is even number, so it is also a boson. Okay, same in this. Okay, so 2H, 22Na and 18O, nucleus of all these are boson, but electron is not. In the next option, photon is a boson, nucleus of 2H is a boson, nucleus of Na is 22Na is boson, nucleus of 18O8 is boson. So option 2 is correct. In option 3, proton is not a boson, so this is not correct. And in option D, this nucleus of 17O8 is not a boson, because there are even number odd number of fermions into it. So option 2 is correct. Next question. Consider a gas made up of two identical particles. And suppose that each particle can be in one of four possible quantum states. So there are 4 quantum states are given. In case of Fermi-Dirac statistic, what will be the probability of having both the particle in the same state? So again, this is for Fermi-Dirac statistics, there is a restriction. No two particles can have same state. So again, this is 0, probability is 0. Now to the next question, question number 6. Fermi function Fe is given, and the probability of occupation, this Fe gives the probability of occupation of electron per energy state. Then the probability of number of electron at absolute temperature T is equal to 0 when E is equal to EF is. So again, this is near 0, not exactly 0, but near 0. So f of E is equals to, again this E is equal to EF, so this is equal to 1 over e to the power 0 plus 5. So e to the power 0 is 1, so the probability is 1 over 6. Probability is 1 over 6. So this was the curve actually that define the values. So this is 100% occupancy, like this is 1. 100% occupancy means 1, and this is 0, and this is half occupancy, and this half occupancy is for this all the curves at E is equal to mu, when Fermi energy is equal to E energy, E is equal to energy of state, then this occupation number is half. But for this at temperature T is equal to 0, this value is 1. Yeah. So this is the graph. So at temperature T is equal to 0, when E is less than mu, then occupancy is 1. So in this state occupancy is 1, and when this E is greater than mu, then occupation is 0. There 0, there 1. So this is the curve. So in all these energy state, the occupation is 1, and in all these occupation state, occupation is 0. All these energy state. Thank you. But I will not leave the meeting now. Actually, I will discuss some more about this classical thermodynamics because I could not get much questions regarding this concept, and I have explained this concept in very detail. So if you find any question, you can easily solve the questions. And I'll take a short break, and after that we will start this formula for this classical thermodynamics. And before that, I'll again explain. I have explained in my last lectures as well this distribution, these microstates. So I'll discuss these microstates, and after that some formula of classical thermodynamics. So if you have any problem, you can ask, and I'll be here in the meeting only, and we will meet in 2 minutes again. So now we again will start and we'll revise the formulas. Do it, start it. Why? I think, give me a minute. Okay, I'm having some problem in the internet. Okay, give me a minute and I'll solve it, and again we'll start. So okay, now let's discuss some formula, all formulas that we have already discussed. So first of all, let's discuss this distributions. Okay, I think let me share my screen. So here let's now discuss about this microstates in all the distributions, Boltzmann and this Bose-Einstein and Fermi-Dirac. So we have already discussed this, so now again for this W, for Boltzmann, W is equals to, W is my number of microstates, so W is equals to n factorial, n is total number of particles, and multiplication of Gi to the power Ni. Gi is the degeneracy and Ni is the number of particles in ith state, and this Ni factorial. So this is for Boltzmann distribution. So let's take an example. Let's say there are 6 particles distributed in let's say 4 states, and each states have, let's say, 1, 2, 2 and 1. Let's say these are the occupation number. Of respective states, like for state 1, 2, 3 and 4. So we can calculate W as total number of particles 6 factorial, and the occupation, these are the occupation number, and the degeneracy, let's say degeneracy are 2, 3, 2, 1, let's say. So these are the degeneracies. So this can be Gi to the power Ni. So these are the degeneracy to the power occupation is 1, 2 to the power 1 divided by Ni. Ni is 1 factorial, multiplication by other, this 3 to the power 2 divided by 2 factorial, and this 2 to the power 2 divided by 2 factorial, and this 1 to the power 1 divided by 1 factorial. So this is 1 only. So this is 6 factorial into 2 into 3 into 3 9 into 4 divided by 1 factorial is 1, 2 factorial is 2 and 2. So this is 6 factorial into 18. So these are the number of microstates according to Boltzmann distribution. In Bose-Einstein, and we know that in Boltzmann there is no restriction on the particles. Many particles can fill a state, but we can, if we have given some restriction, so that will give according to this. So these are the microstates. And for Bose-Einstein, let's say there are m number of states and n number of particles. Then this W is equals to n plus m minus 1 factorial divided by n factorial m minus 1 factorial. So this is Bose-Einstein statistics. And no restriction on particles. So now this Fermi-Dirac, according to Fermi-Dirac, W is mCn, this m number of state and n number of particle. So this is m factorial divided by n factorial m minus n factorial. So these are the very important formulas for this calculating the microstates. Let's say there are 10 states and 5 particles. So the W is 10 factorial divided by 5 factorial. 10 minus 5 is 5 factorial. So this is 10 into 9 into 8 into 7 into 6 divided by into 5 factorial divided by 5 factorial into 5 factorial. So this will cancel out, and this is 10 into 9 into 8 into 7 into 6 divided by 5 into 4 into 3 into 2. So this 3 into 2 is 6, and this 5 into 4 is 20, and this will be like this. So 9 into 7 into 4. This is the answer. Similarly, we can take an example for this. Let's say we have taken same example for this. So W is 10 plus 5 minus 1 factorial divided by number of particles are 5 factorial and 9 factorial. So this is 14 factorial divided by 5 factorial 9 factorial. So we can solve this and get the answer. We can notice that microstates are more for this Bose-Einstein with same number of state and same number of particles. Now let's quickly revise some formulas regarding this classical thermodynamics. So first of all, that state function like they only depend on the state, initial and final state, and how they are reaching to that state, it does not matter for them. Like there can be many paths, path 1, path 2 and path 3. If it is a state function, then it will not depend on the path and it will only depend on the initial and final conditions, and for all three that function will give the same value only. So these are the state functions. And square integral of those state function closed integration is like from, if we are going from path 1 and coming back to the same initial point from path 2, then its value is 0. So its closed integral is equals to 0. And the main property is that they are exact differentials. And if let's say it is a function f and we differentiate it with respect to y first and then differentiate whole function with respect to x, it should be equals to, if we differentiate with respect to x first and y in the last. So this is the main property of this state function. And another main this thing for this thermodynamics is Maxwell equations. So we know this Maxwell square and we can calculate all the thermodynamic property from there. So it is S P Vt Hg Au. So first of all, let's say we are calculating this dH. So dH is related to this ds and dp. So dH is related to this ds and dp. There are s and p. So from s we are going through this line, this arrow. So it is going to t. So it is t ds. From p we are going through this arrow and we are going to v. So it is v dp. Now check the signs. If we are going, if the arrow is pointing to that property, this v and t, arrow is pointing towards p, v and t. So these are all positives quantity both. So this is t ds plus v dp for dh. Now for dg, this dp and dt will be important. So dp and dt. So dg for this p, while going through this arrow, this is going to v. So and arrow is pointing towards v, so it is positive. So it is plus v dp. And from t, when we are going to s, so arrow is towards t, not towards s. So it is minus s dt. So this is dg, v dp minus s dt. Now dA is dv dt. Now from v we are going to p and arrow is not toward p, so it is minus p. And from t we are going to s and again the arrow is not pointing toward s, so it is again negative. So this is minus p dv minus s dt. Now du. So du is now ds and dv. So from s we are going to t, so it is positive as arrow is pointing toward t. And from v we are going to p, but arrow is not towards p, so it is minus p. So these are the equations for ds, dg, da and du. These are all state functions. So by these functions we can calculate all other functions as well. Like let's say if we have to calculate curl H by curl, let's say curl P at constant entropy is equals to curl H by curl P at constant entropy is equals to, this is 0 and so this is equals to V. Okay, like this we can calculate other quantities as well. So now let's move to the next thing, equation of state. So there are two equation of state. First equation of state is curl U by curl V at constant temperature T. U is internal energy and V is the volume at T at constant temperature T is equal to T curl P by curl T at constant volume V minus P. And the second equation of state is curl H by curl P at constant temperature T is equals to minus T curl V by curl T at constant P plus V. So we can see that the first equation of state have the equation this has the unit of pressure, and this second equation of state has the unit of volume. So these equation of state are applied to every gas equation, every gas, like for ideal gas, both of these quantity will be 0. Curl U by curl V at constant temperature and curl H by curl P at constant temperature, both are 0, because we know that U and H are the function of temperature, and at constant temperature this both of these quantity will be 0. These are the for ideal gas only. Now let's say we have equation P again. Sorry, network was lost, so give me a minute. So where were we? These equation of state we have solved. So I was taking an example. P v minus nb is equals to nRT. So what will be value of curl u by curl v at constant temperature and curl h by curl p at constant temperature for these two. So just now we have written the formula curl u by curl v at constant temperature T is equals to equation of state, first equation of state, T curl p by curl T at constant volume minus P. So by putting these values, so curl p by curl T for this equation. So P is equals to nRT by v minus nb. So curl p by curl T at constant volume is n divided by v minus nb r, and putting the value here, nRT divided by v minus nb minus p, and we know that p is equals to nRT by v minus nb, so this is equals to 0. So curl u by curl v for this equation, equation 1, is equals to 0. Now calculate curl h by curl p at constant temperature T, and we know this is equals to minus of T curl v by curl T at constant pressure P plus v. So now v minus nb is equals to nRT by p. Differentiating it with respect to temperature T, so this will give curl v by curl T at constant temperature P, and this will be 0, well, as these are the constant terms. So this is nR by P. Differentiating with respect to temperature, this will give this value. So this is nR by P, so minus nRT by P plus V. So this is nRT by P is equals to V minus NB, nRT by P is equals to V minus NB. So this is minus V plus NB plus V. So the answer is NB. So it is equal, not equal to 0. So curl V by curl T at constant pressure P is equals to NB. So what we get here? So ultimately what we get here, this curl U by curl V at constant temperature T is not 0, but curl H by curl P at constant temperature T is NB, and NB is nothing but the excluded volume. So what we get here, curl U by curl T at constant pressure, constant volume V, I have written it wrong, curl U by curl V at constant temperature T is equals to 0, but curl H by curl P at constant temperature T is equals to NB for this equation. P V minus NB is equals to nRT. But for ideal gas, we can calculate this also, but you can take it as an homework. For PV is equal to nRT, equation of state, both equation of state are equals to 0. You can calculate for PV is equal to nRT. For PV is equal to nRT, calculate equation of state. So now we move to this cyclic rule, very important for thermodynamics and applied to all the gas equations, all the gas like ideal, real, anything. So but first of all we should know this cyclic rule. This is x, y and z, and it is clockwise. So curl x by curl y at constant z, curl y by curl z at constant x, and curl z by curl x at constant y is equals to -1. This is the cyclic rule. So now the compressibility factor. Z. So that Z is equals to PV upon RT. So if it is equal to 1, this is an ideal gas, and if it is not equal to 1, then it is a real gas. And we say that deviation from ideal gas, ideal behavior. Heat capacity, Cp and Cv, and Cp and Cv for monatomic, diatomic gases, we can consider this also. So we know that degree of freedom is (3m). I have done this also in previous class. So degree of freedom is 3n, and for translation there are 3 degrees of freedom. They can move in x, y and z direction, so there are 3 degrees of freedom for translation. For rotation, there may be, for linear, degree of freedom are 2, and for non-linear, degree of freedom is 3. And for rotation, sorry, for vibration linear and non-linear. So in the linear, so degree of freedom we can calculate now from here. We know that total degree of freedom are 3n, and out of this 3 are translation, and for linear 2 are rotation, so rest are this vibration only. So vibration will be 3n minus 5 for linear and 3n minus 6 for non-linear. Okay. and contribution to CV per degree freedom is R by 2 for this and R by 2 for this, R by 2, and for vibration it is R and R. So this is at high temperature, but at low temperature we consider it as 0. Contribution for this is 0, for vibration is 0. So now using this we can calculate the value of CV and CP. As we know that Cp minus Cv is equal to nR, and for 1 mole it is Cp minus Cv is equal to R. Cp minus Cv is equal to R for ideal gas only. 1 mole, molar. Okay. For monatomic gas, we know that there are no rotation and vibration possible in a single molecule. So because it only can translate. So these are all not considered. So the value of CV is 3 into R by 2. So 3 by 2 R. CV is 3 by 2 R for this. This is the contribution R by 2, and this is the degree of freedom. So multiplying this to 3 R by 2 for monatomic gas. And Cp minus Cv is equal to nR. Cp minus Cv is equal to R. So Cp is Cv plus R. So it is 3 by 2 R plus R. So it is 5 by 2 R. This is for monatomic gas. For diatomic gas, let's say this. So for the diatomic, this is contribution from translation is 3R by 2. Now from rotation it is R. So from translation it is 3 by 2 R, as we already calculated this, and from rotation it is 2 into R by 2, it is R. And now about the vibration, so it is diatomic, so N is 2, so total 6 degree of freedom, out of which 3 and 2 are taken into translation and rotation. Only 1 degree of freedom is remaining, so that is plus R, linear, that is plus R for 1. So this is equals to, at the I am calculating it as high temperature. At high temperature for diatomic gas, this is equals to 2R plus 3 by 2R. This is 2243 7 by 2 R CV at high temperature. At low temperature, CV is equals to, there is no vibration contribution, so 3 by 2 R plus R, this is equal to 5 by 2 R. And now Cp is equals to 7 by 2 R for at low temperature, and 7 to 9 by 2 R at high temperature. Okay, like this we can calculate for any gaseous molecule. We can calculate this CV and Cp. It is very simple by using this chart. And what else we can discuss here is, this entropy formulas we can discuss. What time is there? Okay, we have some time now. So we can discuss this entropy formula as well. Okay, we will discuss this entropy formula only. Or we also, that first law of thermodynamics, I don't think that we need to discuss that. We know that already. So okay, I'll discuss these formulas for entropy. So first, for reversible ideal gas, for reversible ideal gas, so delta S is equals to N CV ln T2 by T1 plus NR ln V2 by V1. If temperature and volume are given, we can use this formula. And if temperature and pressure are given, then this is equal to NCP ln T2 by T1 minus NR ln P2 by V1. This is when temperature and pressure are given. For isothermal process, isothermal reversible process, delta S is equals to, for we know that if temperature is same, so T2 and T1 is same, so ln1 is 0, so this quantity will become 0, this quantity also become 0, so this is equals to NR ln V2 by V1, that is equals to minus NR ln P2 by V1 when delta T is equals to 0, change in temperature is 0. Okay. For phase transformation, let's say this water liquid is changing into water solid, ice, so, or solid to liquid. Okay, so delta S will be equal to Q by T, so that is equals to delta H of transition divided by temperature of transition. So transition here is from liquid to solid, this is fusion, so this is delta H of F and T of F. And let's say we are going from water solid to water liquid, sorry, water solid to water gas. And we are going through, like, let's say okay, let's say this is solid to liquid, like, let's say, and from we are coming from minus 20 degrees Celsius to liquid, let's say 20 degrees Celsius. So first from minus 20 degrees Celsius to 0 degrees Celsius, it is a we calculate delta S1, and then at 0 degrees Celsius there is a phase transition, so we calculate delta S2, and from 0 degree Celsius to 20 degree Celsius, we again calculate delta S3. So entropy is additive, so delta S is equal to delta S1 plus delta S2 plus delta S3. We have done many questions with this concept, so we know this. So for delta S1 and delta S3, we can apply the simple formula, this for this reversible ideal gas delta S, these formulas. And for this delta S2, we only need to apply delta H of transition divided by T of transition, and rest are this same. So like this we can solve such problems. So I think that's all I wanted to teach today. And if you have any problem, you can ask me. I'll be here for next 5 minutes, and then I will leave the meeting. If you have any problem, you can ask, or you may leave the meeting as well. Thank you. I'll be waiting for next 5 minutes, and then I'll leave the meeting. Thank you.